Hey, what's up? I'm Tim, and I'm out here on a beautiful Wednesday night doing one of the things I like to do best. Let's get nerdy. I'm going to bring you with me. So what I'm currently doing, as I had promised, is continuing to make Pico 1 even more betterer. I'm currently working on a racing variant propulsor, and the objective of that is to really push the motor and battery pack to its limits to be able to offer the highest axial velocity and thrust possible from this little 20mm drive. So here we go. There are a couple important little things to know. So this thing has an impeller spinning inside of it. The impeller is pretty much just like a boat propeller, but on the inside of a ducted system. This impeller setup is a little bit unique in the sense it doesn't have like a bunch of blades hanging off of it. It just has two blades. They're like swept blades, kind of like a screw almost. And then of course it is broken into two stages. So there is a gap in between. There's like a cutout per se between in the middle of that blade sweep to allow for impeller stator vane elements, which are really important for self-priming. Which is a little outside of the scope and scale of this video, but maybe in another one. So just know that this impeller functions kind of like a screw, or like one of those old, gosh, what are those, Archimedes screws, where they picked up water with that big screw, creepy looking thing. Kind of the same thing, but instead of picking up water, it's accelerating water. So the impeller, well, there's really two ways, well, there's really three ways to make a jet drive shoot the jet out faster. And the first way is to make it go faster, to make it spin faster. We can't do that because we're limited by the laws of little baby motors and batteries. The second way is to shrink the nozzle. By shrinking the nozzle, you increase the velocity of the jet because fluid is incompressible. And in this case, you essentially have fluid that comes up in here, and then this right here is spinning super fast, forcing water through. It's creating like a stampede of water. And then it gets down in here, and this water has nowhere to go. It can't go back because there's already more water being forced up in here. So the only way that it has to go is out the nozzle, or a little bit up into the cooling port, but that has a pretty well-defined volume, and there can only be so much that can run through that. So fluid just has to go out this nozzle. And because it can't compress, all it can do is speed up so it can get the hell out of the way of the water behind it and get out of the nozzle. So by shrinking the nozzle, we make that stampede file through there faster. However, at the end of the day, because the nozzle has a smaller area, less fluid can go through it at any given point in time. Now, thrust at its core is really just mass flow rate multiplied by the velocity at which the fluid leaves. In newtons, anyway, that's how you determine that. So, the long and short of it is, by shrinking the nozzle, you gain speed, but you lose thrust. And that's just the way that the world works. The third way to be able to increase the both thrust and the speed at which the jet exits the nozzle velocity is to make the impeller profile pitch more aggressive, to make that kind of screw blade more a steeper angle toward the trailing edge of the impeller, the end of the impeller, like in stage 2, because stage 1 has a less severe angle that it uses to scoop up water, so we need that. But stage 2 is really in charge of propelling the fluid, and yeah, so we can increase the pitch on that. So that's what I'm doing. I'm increasing the pitch of stage 2 on the impeller. But the challenging part is that the impeller doesn't live in a vacuum. Everything impacts everything in the propulsor. So as fluid gets spun up through that impeller and forced out at a higher velocity, the rotation of that impeller is also imparting angular momentum, or swirl, into the fluid itself. Now, if you think about those videos of like some kid that's on like a merry-go-round that has a dirt bike wheel attached to it and it's spun up way too fast and they get shot off into outer space, same thing happens with the fluid in this drive. So if there's, after the water goes through this impeller, it's spinning rapidly. If it's still spinning as it reaches this nozzle, the jet fans out. And that's bad for business for us, because what we see, what is really good for making our vessel go fast, is water that is being shot out directly opposite of the direction that our boat is traveling. So if water is spraying up and down and all around, that is not helping us go faster. That's just wasted energy. And that is the resultant factor, the result of too much swirl. So what helps get rid of that, you say? Because that video you posted in my Pico one has this nice tight jet. Well, it's all here in this diffuser. This is the area, the diffuser and nozzle, this component right here. And it has these vanes in it. And these vanes their job is to intercept that swirling fluid at the angle that it is swirling at, and then curve and straighten that fluid out. So it's kind of gently pushing it from being rotating into a straight line. It's like a nice little set of guide rails for it. Now, that angle at which the fluid contacts the impeller, the angle at which the fluid contacts pretty much anything is called the angle of incidence. Now that angle of incidence changes with the speed of the impeller. The angle of incidence really changes when you change the actual angle of the impeller pitch profile, because if the fluid is being scooped up at a more severe angle, that angle of incidence that it's coming into this diffuser at is going to be steeper as well. And we need to match that perfectly to be able to capture as much energy as we can and to be able to redirect it into thrust and velocity. So that's what I'm doing right now. I made the changes to the impeller pitch profile, and now I'm just doing a whole bunch of CFD testing with very small things like this. This angle on these vanes has like an angle of attack, the angle, and that is a parameter that I can adjust. So I'm making it this, and then I'm running a test, and then I'm putting in my Excel sheet, and then I'm changing it a little bit, and then I run another test, and I love this shit. God, I love this shit, and I'm really excited to be able to bring this race profile to you.